Welcome everybody, DevHeads Office Hours. We skipped last week for the first time. I was going back and looking. I was like, wow, we had a nice little run there. Skipped last week, but we're going to get back in the saddle with a little bit of a caveat. I'm talking to a couple of people about the fact that they're going to be in and out. How summer holidays are coming up, so we may reduce the frequency. We may start going to every other week. But I'll let you guys know, and we can confirm that, and then pick back up, obviously, in the fall when things start, when everybody's around and things start jamming again. But nevertheless, here's our agenda. As always, we're going to do welcome and introductions. Then today's discussion is around more on Zephyr. Zephyr is becoming a very popular RTOS option. We had a little bit of an introduction to it from Zach a couple weeks back, and we're going to continue on with that exploration, looking into threading and priorities today. After Zach gets through his deck, which is really awesome, I've had a chance to page through it, so you want to stick around. We'll get into some community questions, which are very few because we've been doing a pretty good job helping each other out. We'll dive into a couple of those, and then what can we do to get better by 1% next week, and then any asks and gets anybody else from the community, and then the outro. So welcomes and intros, who we are. Hi, my name is Brandon. I've been a tech journalist for about 15 years. I really enjoy being part of this community DevHeads. Like everybody I've met, I feel honored and privileged. And now I'll pass it off to Umesh.
Hello, everyone. So I'm Umesh from Pune, India, and I've been building embedded software and hardware from past almost like 10 years for IoT solutions. Thank you.
Very good. Zach, you want to say hi?
Hey, hi everyone. I'm Zach from Cape Town, South Africa, and I've been a developer for quite, I think, 10 years as well, from a bit more than that. But yeah, really glad to be joining on the weekly DevHead sessions, for sure.
Cool.
Thank you.
Ming, your turn.
So I'm Ming from France. I've been playing around with Linux for about 30 years and embedded Linux for about 15 years now.
Awesome. Thanks a lot. Good to have you. Hemel, you want to say hi? Maybe he wants to say hi, but the internet doesn't want him to. Everybody else, if you are in the either on LinkedIn or you're in the platform and you are not on camera or audio or mic, feel free to drop a message in the chat and just say hi. Glad to have you, and yeah, we'll carry the conversation on over there. So today's topic, as I mentioned a little bit before, Zach has been messing around with Zephyr. It's a new RTOS, and I do that in kind of air quotes because there are a lot of Linux type features about it, especially around the build system, etc. So if you're a Linux user, it's a little bit more familiar than you'd probably get to say you were going to jump straight into FreeRTOS or VxWorks or ThreadX or something like that. But it still is small. I mean, it's used for, I think Zach was telling me it could get down to 2K if you stripped everything out. It's used for resource constrained devices. It's also been positioned to make it easier for connected devices to get connected. So that was one of the claims to fame of Zephyr. And as he's written here, it's really good for wireless gateways, wearables, etc., sensor fusion applications. Of course, if you're going to have a use case like that, it's likely that you're going to have multiple threads, and those threads are going to have to share resources, and that's when you start needing prioritization and threading and scheduling and things like that. So that's what Zach's going to walk us through today, is his exploration of Zephyr in that context. If you have any questions, feel free to drop them in the chat function, whatever platform you're on, and I'll be moving around trying to answer those and make sure that they get addressed. So without further ado, Zach, do you want to take it away?
I'm muted as always. So yeah, like Brandon said, so if you're the kind of person who's looking into Zephyr, you're probably looking into Zephyr having you have a lot of threads or more than one thread in your application, and you need to possibly be able to determine how those threads are going to be scheduled and in a way that you can predict yourself. So the slide we have right now kind of shows the shortcomings of just using priorities. And we have like the typical case of inversion of control here. This is from, I think, Making Embedded System by Alicia White or something. But basically what she explains here is you'd have a low priority thread or task going on, and then a high priority task would get ready, and it would preempt the microcontroller and start working, but it would realize it needed a resource that the low priority task needs to release, and it would yield back to this priority task. But then when that would happen, that low priority task could end up being preempted by a medium priority task, and just like that, you've lost control, or rather your high priority task has been preempted by a lower priority task. And this is why you would need a scheduler, or a scheduler the kind that Zephyr provides for us. And I think we can go to the next slide. Or should I wait just a moment? Yeah.
Yep, I got it. Just say next slide and I'll push it.
Next slide. Okay, cool. So that's easy. So yeah, as like most of the other threads in real-time systems. So threads have their own allocated stack area. This is statically allocated. Zephyr does not provide for dynamically allocated threads, and the kernel handles each thread by itself, so you don't have any sort of like leakages of data. Threads have an entry point that could exit, which would mean the thread is basically terminating, and it's a function. And then you can provide a priority when you're building a thread, and there's options for making a thread getting treated as a special thread. Basically, you can move between types and priorities of threads, and we'll see this somewhere along down the line. You can go to the next slide, I think. So yes, this kind of shows how Zephyr's scheduler deals with threads. When you create, there's a few states here. You have a created state, you have a ready state, you have a running state, and you have all the like sleeping, suspended, waiting, and the dead states, aborted and terminated. So whenever a thread, the important part to see about in this slide is whenever a thread transitions into or out of a state, that is something Zephyr refers to as a reschedule point. A reschedule point is what Zephyr uses to choose the next thread, rather than fixed time slices, like time intervals, like rather than having a sysdig every time. Every time we get into a reschedule point, basically a thread goes out of a ready state or into a ready state. A thread becomes ready. A thread waits for a kernel object or receives a thing it was waiting for. These are moments in time where Zephyr can now do a reschedule rather than running interval reschedules. I think we can move to the next slide. Sure. Yeah, so this is kind of something I was hinting to in the previous slide. So you can define rules of how threads will move from one to the other. Zephyr's kernel provides context switching, which is where it kind of copies the registers, the stack as a thread is using it, and places it aside, and then it would yield control to something else. And then when it would come back, it would basically reboot that thread where it was, and you would have the resources that you had. And you can't temporarily lock the scheduler at certain points. And when you do this, it's your duty to unlock the scheduler. But then if your thread does one of those things where a reschedule point occurs, like if you lock the scheduler and then you go into some wait state, the scheduler can, this is a reschedule point, it has occurred, and there's no guarantee that it'll come back straight to your thread, unless you have some rules, like you've made the thread a cooperative thread or something in such a way that it can't be preempted and it can come back to that. And then whenever two threads become ready and they are of the same priority, the Zephyr scheduler can use either the thread that's been waiting the longest to choose whichever one is going to go next, or optionally we have a way of setting thread deadlines, and whichever one has an earlier deadline, the Zephyr scheduler will use this. And as we spoke earlier, rescheduling points in a tick as well. So instead of going with every time slice, basically as those software options occur, the Zephyr scheduler can basically jump in between. And I think in the next slide, we can look at an example of context switching from. So here we can see thread A starts, but then a higher priority thread becomes ready. And once that happens, the kernel will copy the program counter, the stack pointer, all the registers are 0. I think it's usually 7, and it will put them aside, work on thread B. And then when that's done, it will copy back the context that it was using and go on with thread B for that. Hopefully I'm not rushing through this. Okay, cool. So Zephyr's scheduler modes. So you can, Zephyr comes with quite a bit of pre-written code that can do quite a lot of work that traditionally you would have to write for yourself. And the scheduler basically comes with 3 major modes, but there are options that will enable you to kind of make more modes based on other sub options. So you have you can configure it as a DAM scheduler, which means it has an order list, and it's maintaining a list that it's time slicing through. And basically, this is kind of what we're used to at the moment. It's time slicing through this list, and it has a fast concept switch time, and it's basically, this option can really save you a lot of code, or because it's implemented in quite like skinny way. And then so using it, you can save people have seen up to 2 kilobytes of code saved from using this option. And then you have a scalable scheduler, which is maintains a red-black tree, which is a balanced binary tree of the ready and unready threads and how you feed them into. Obviously, this comes with a lot of overhead in code, more than the DAM scheduler, but this scales up into the thousands of threads really well. Ideally, you would use this where you have more than 20 threads coming into the ready state at the point. The DAM scheduler is good for when you have like maybe a maximum of, I'm trying to remember, a maximum of say 3 threads coming into the ready state at once, and the DAM scheduler works better. And then we have the traditional multi-queue, which is you have a group of lists of priorities. Basically, the Zephyr scheduler will maintain one list per one priority of thread that you have. And this obviously this will come up with a lot of overhead. You need a lot of RAM. You need quite a lot of space to get this run, because it's going to run a bunch of lists for your threads. I think that's most of the major scheduler modes that we have in Zephyr exploit. And you can look at the next one. I wonder what's there. Yeah. Cool. So here we can look at how to understand how the Zephyr scheduler works. You kind of you need to understand how it treats different types of threads. So you have preemptible threads. Preemptible threads are these are threads with a positive priority, and the larger the number, the lower the priority. And what that means is if a more important thread comes along, it'll preempt the current thread. So as we are seeing here, like there's a low priority thread 1 running, thread 2 becomes ready, which is a bit of higher priority. It runs for a bit, thread 3 becomes ready. This preempts, we finish it, and then as you see, when it completes, a reschedule point occurs. And all those preemption points, they're also reschedule points. As a thread yields control, that's also those are also reschedule points. So you can have this version, and you can control you can have this kind of scheduling by having preemptible threads, and these are threads with positive priorities, basically. I think if the next one should show us cooperative ones. Yes. So cooperative threads are the same as preemptible threads. The only difference is they have a negative priority, and they're good for like stuff that needs to happen with deadlines. So assuming you're building like something with a lot of networking in it, and you need to handle, you need to quickly like, if say you have like an Ethernet message or an Ethernet packet coming, you need to copy the data quickly, put it in some sort of buffer where you can handle it in software, maybe do some response or something, just like send a flag to say you've seen it, you've seen the data, and then process it later. So this is where cooperative threads become easy, become good. And an interrupt can interrupt them or can stop them. Sorry for using the word interrupt twice. Can stop them, but then the control will go back to this very same thread after the interrupt has done the work it needs to have. And when we have cooperative threads and preemptible threads, you can basically have a third type of thread, which is in the next slide. It's basically a meta IRQ. It's in the next slide. You can go to the next slide, which is a meta IRQ thread. This is what happens when you have a thread that needs to basically, after say, like the thread I was explaining earlier. So you have an Ethernet packet coming. You need to do something immediately after the packet has come in before you're handing over to the thread that was going on. And this is called, like, would be the top half of your driver. So you'd copy buffers, you would alert who needs to be alerted, you would move the data into somewhere you can work on it later. And then you would, after doing that, you would yield back to the thread that was running. And then that would also, once that is done, it would yield back to your important thread, say, finishing the networking thing that came through. So if you combine cooperative and preemptible threads, that you come up with this meta IRQ threads. They're quite tricky. It's not recommended to use them everywhere. And it's basically, they're not to be used as just very important threads. You could end up, I guess, in some sort of weird ways, you could end up with the inversion of control thing again, if you're not careful with the way, if you're willy-nilly with making meta IRQ threads. And the way you make meta IRQ priorities is basically when they're like, they're negative ones, but you can have them, you can give the thread options to make them, to identify as one of these meta IRQ threads. Okay, so we can go to the next one. Okay, good. So number of priorities in Zephyr. So traditionally you come with, I think, 32, because there's 15 positive ones and 16 unpositive ones plus a 0. So you have 32, but these are configurable and they're only limited to how much RAM you have. So you can have realistically all the way up to 256, I think. But traditionally, I think I tried to look around to see how many other people have the most interrupts. There's people with crazy amounts, but the traditional number comes to around 30, and that should accommodate to this. The main thread runs at a priority of 0, and then we have utilities in Zephyr that can help us, can aid us change the types of threads and their priorities. Basically, you can change a type of a thread by changing its priorities on the fly. So a cooperative thread can become a preemptive thread, and a preemptive thread can become a cooperative thread on the fly as needed by your application and such. We can look at the next slide. Hope I'm not rushing. So this is how you create a thread. You basically would provide the name of a thread, the size in bytes for the thread. You provide an entry function, and then you have space to provide 3 parameters that are the parameters for your entry function. Then you have a priority, then you have kernel options for special treatment, and then you have delay. So the delay, actually here, the delay is one of those things, if you remember the chart that showed all the states of the threads. So this delay is one of those things that could cause, if you observe the delay here, it could cause a reschedule point, which is one of those things that Zephyr uses instead of system ticks. So reschedule point, by this thread becoming ready, like this thread. This thread has a 0 delay before start. So as soon as it starts, it's going to be ready. And this would cause a reschedule point. Let's look at the next one, I think. Yeah. So passing, okay, so we've looked at scheduling. We've looked at how the scheduler works. There's a small part of scheduling that is, how do you pass messages between threads? And Zephyr provides two major ways of doing this. So we can maintain message queues. So this same size containers list, same size list of containers. And this messages, this containers can be filled with messages, and then we can pass this messages around. Basically, you can have a number of message. You can have as many message queues as you want, limited by RAM, of course, and the RAM handles each of the message queues by itself. Basically, you tell it how many items you want in the queue. You tell it the size of an item, and then you give it an alignment, and then the kernel makes the queue for you. You don't go around making the queue for yourself and such. But there is utilities for you if you need to do that. So if you're making a lot of like things that work with streaming, you'll need back pressure, and this is where your consuming thread needs a way of communicating to your producing thread that, like, hey, I'm still consuming the thing that you're giving me, so I can't go yet. And Zephyr has like those has utilities. When you're making a thread, you can tell it, say, wait until there's something in this message queue and before you're ready. And then you can also go you can do this in sort of like a stage version. So basically, maybe you have 5 threads. Let's consider you have a thread that reacts to a sensor, and then some processing. You do some signal processing, and then you give this bit of thing to another thread that puts that as a feedback into something else. This, you can daisy chain them so that they wait for each other. I won't go until someone gets data, and then once they get data, I won't go until they yield to me, and such and so. So you have mechanisms to handle back pressure, which I found to be very interesting at such a low level, because I've only had to deal with back pressure at like quite like a high data rate in web, but I guess it occurs here as well. So they pass data to the highest priority waiting thread that consumes from that queue. So almost like a mini scheduler. And then the kernel's internal implementation of message queues is ring buffer, I think, which is a cyclic buffer. I think the next slide will show us how to create a message. Oh, no, that's just a visualization of how this producers and consumers work. The next slide, should show us how to make a message queue. The next slide, please. Sorry. So here you can see we have some sort of accelerometer reading. We make a struct with it. We have all of this code is going to be available later. So we have some sort of accelerometer reader. We with this reading, we use this reading to construct our message queue. We give the name of the queue. We give the size of each item in the queue. We need how many items we want, and then the alignment of queue items, and the kernel will handle all the rest for us. It will allocate, it will do all of that for us, and we don't have to do much after that. So that's how easy it is to make message queues. And then the next kind of way of passing data between queues, or rather between threads, sorry, is FIFO, like a fast in, fast out register. The advantage of this over the other one is you can handle multiple size, variable size data. So say you are receiving data through, you have this application that sees strings through UART, and you don't know what the size of the string is going to be before. So instead of using the other one, instead of using the message queue that we were using before, you would use a fast in, fast out buffer, and they don't need a size specification because you would allocate some space on the heap for them, and you would use the kconfig for this. And then since it only holds addresses to the items, the number of items can change and is only limited by the area you set for the fast in, fast out structure. They're easy to misuse, so I included the use with care here. This is what I've seen. But you would basically use this as your, we saw an image before that had a producer and then a message queue and then a consumer at the end. You would use the FIFO or the fast in, fast out structure as the way I see it. You would use it at the edge where you don't know what kind of data is coming in and what kind of what size of the data is it going to be, and then after that you'd basically pipe it into whichever message queue you would want. So you would have a number of threads waiting on a number of message queues, but they all kind of stem from this root collector that is based on a fast in, fast out structure. I think we can look at the next. It's just an image that's showing that. That's fine. Me trying to be as explicit as I can be. There's a couple of missing ones. There's in any case, there's a slide. There should be a slide that shows a table, which is a comparison between Zephyr and the other RTOS systems, basically. Their minimal footprints and their typical footprints and how many priority levels are available. So I can speak through this quickly and then we'll jump into a code demo that we'll look at.
Oh, hold on, let me see if I can pull that up.
Just forward to 2 slides, the third one from there.
Yeah, that's
Yeah.
cool. It could be that.
Just move 2 slides up and
Yeah. So yeah, we have a table here and it shows the typical stuff, typical observed use cases. Of course, this is not like farm hard truth, and this is has to be like you, depending on what you're doing and how you're doing it, you could achieve better performance than this or worse. Your mileage might vary. That's the internet term for this. So as you can see, Zephyr comes around like one of the smallest of the popular ones that I looked at. I could have looked at more, but these are the ones we thought about with Brandon. Sorry. But so Zephyr is kind of the mid-range, and it can be pushed to lower, like 2 KB I've seen. But that was a very skinny application. You can use the kconfig options to disable as many almost peripherals and almost systems that you don't need and end up with a very small image. But the typical footprint comes to around 50 KB, and this is basically either the top, one of the averages. As you can see, most typical footprints either end at or start at 50 kilobytes. Like I said, Zephyr has a number of configurable priorities, and you can go, I think it's limited to like the number, how big of a number you can have on your system. And then you can see with FreeRTOS, we have all the way up to 256. With VxWorks, we have 250 up to 256. Yeah. There's a cost from Nordic that goes through all of this, which is a lot of the places I got most of the information from. And yeah, and the example priorities column at the end is basically what people have observed in the wild. We can look at a code example, but I can also basically take questions as I try and show this example. It's very simplistic. I tried to have as few lines as possible so that I could focus on understanding why rather than do a code demo of this is how you do this in code and such. The aim of today is to discuss the scheduler and know why to choose it or not. Yeah, let's do any questions before I share my screen for this.
Yeah, Ming actually had a question about priority inversion. Let me go back up to it. It's just basically how does Zephyr deal with priority inversion? I'm not sure if you got that far into it yet.
Well, it would be by you would have to make the rules. You would have to make the rules. So you would need to build your threads so they're either like cooperative or collaborative, and it depends on how you're using. So you would make. Could we go back to the? There's a slide at the end. There's one of the slides for cooperative stuff. Yeah. Because you are in charge of the scheduler by setting your priorities, and your priorities in turn determine whether your thread is preemptible or not. You could envision a world where you plan out your threads well enough before you implement them that you end up in a place where you have it's farther back, Brandon. It's farther back. It's the code. Yeah, one more. I think back. Yeah. So you could. This is ideal. So this is both time sliced and priority sliced. So the scheduler is going around. It's giving time slices. Which you could set it to do. You could set it to go give me enough time slice. So slice my available time in equal time slices between my equal priorities. So we could say here thread 1, 2, and 3 are of equal priorities, and thread 4 is of a higher priority. So what you see here, we have a bunch of preemptible threads, and then we also have the scheduler set in such a way that it's going through and time slicing everything. So, and when it does get to the important thread, it preempts and it goes back into, so it's doing thread 1. It's because instead of systics, we have reschedule points. And if you're not careful, if a thread does not yield or does not go to sleep or wait for a kernel resource, a thread could go on forever and affect threads of higher and equal priorities. So what you want to do is you have a sharp knife here. You need to set your scheduler right, and then you also need to do your priorities right, so that you end up in the same situation in an environment where you preempt whenever is needed, and also you share time as needed so that you don't stay in something for long. I wonder if that answers your question. And I say his name wrong. Is it Ming or Ling?
It's Ming.
Ming. Yeah. How did that come to be, if I might ask? Sorry.
As a quick diversion there, if you look at my full name on screen, the bit that looks like Menzies Runciman, Menzies is not pronounced like Menzies. It's an old Scottish name that is actually pronounced Mingus. So it's shortened down to Ming to try and teach the Sassenachs the correct pronunciation of my name.
Perfect. There you go. Awesome. I don't know if that answers your question. I tried really hard.
Yeah, it does. So it's up to the user to protect against things like
yes. The Zephyr scheduler happens to be a very sharp knife. So you can do anything, and because you can do anything, you can either shoot yourself in the leg or you can do the most awesome thing. Yes. Yeah. Any other questions?
Yeah, there are a few. I'm answering some of them. Here. How many threads can be created in a 32-bit MCU? What are the advantages? When are we able to create and execute functions using the threads? What is the need of multi-core MCUs? So a bunch of layered questions there. One of the things I was going to point out is, in theory, Zephyr says that it supports an unlimited number of threads. You always have 2 threads by default. You
Yes.
know, I think you know, a lot of this is going to depend on your specific use case or application. Some of these questions here, like how many threads can be created in a 32-bit, what are the advantages? I don't know if you want to weigh in on any of that, Zach.
For threads, this is depending on memory usage, and I don't think, I don't know. I have no business calling out your application, but I don't think you're going to, this is a number you're going to run into, like you're going to have some millions of threads and you're going to need them. So this from Zephyr, it's limited by only the space you can allocate them with your RAM, I guess. What was the other question?
Probably
something about 32-bit.
Yeah, I think actually the more pertinent question here is the next one that John posted about what features of the RTOS add up to the footprint that make it variable. In other words, you know, what can you strip out?
Yeah. Yes. So you feature. How do you explain this? You can strip out features. So like I think there's a slide where we're looking at the scheduler modes. And some of those scheduler modes obviously describe a world where there's a lot of code added on top of the real-time system. And such kinds of features, you can strip them out. Yeah, this. So if you don't need a scalable scheduler that grows to thousands of for thousands of threads, and you're going to end up with, like, in some sort of traditional system where you have like 30 or so odd threads, then the DAM scheduler works really, or the traditional multi-queue works really. So this is the kind of, using the K config in Zephyr, you can disable these kinds of things. You're not using logging. Logging comes with a lot of overhead because Zephyr has this thing, like if I just log on my, I'll share code. If I just log on my on Zephyr, it's one of those like, I wonder, yeah, cool. So we can see, like, let's look at, there's okay, in my consumer function, I have a log. Every time I receive information, I run this log. So I'll think I can do something like, let's see. West. No, let's listen on the screen, and then let's West build. Okay, and then we're listening, we're building. I'm quickly just building the code, and what I want to see is logs, and I wanted to show logs because I don't need to do anything special. I just need to write logs, and west flush. Yep, that runs. It's running, and then you'll see we have, from the DevHeads thread, we've got values we're getting values from the queue. So these are all logs from the application, and they're all incrementing. This line of code is here. So my producer function is producing is incrementing the accelerometer values here and just sending them over to my consumer function. But what I wanted to demonstrate in this is when you're adding logs to Zephyr, you register a log module and you add logging here. And in order to do this, to get logging in Zephyr, you would have to enable it with config log, and then I would have to send if I'm using print K, if you're coming from embedded Linux, you have a primitive like print K or stuff, which is like a UI print. So if I'm using something like print K, I would have to configure it to send print K to UART. So because all my logs right now, these logs that we are looking at the moment, are coming in from they're coming in from a little like UART to TTL converter, or rather, I'm getting logs from UART, but I'm not writing code to get logs from UART. All I need to do is to enable a log module, and it will send logs to UART. If I disable the log module, I save code space from the log module. Does this explain how you could strip out features and save components? And you could do this for GPIO, you could do this for floating point unit, you could do this for DSP stuff, you could do this for any sort of features, and you could use the kconfig to pull out stuff or put in stuff as you need it. I hope this explains how you could pull out stuff and make it smaller. Yeah. Next.
There's one super high level abstract question. Why don't we have a unified RTOS? Do you want to take that? It's like the unified field theory of operating systems.
Yeah. Because they always make a unified one, and then the unified one turns out to be the next one. So when you next try to make a unified, that's why we can't have a unified RTOS. It's just humans. Any other questions? Any other questions?
I am going to put into the
John. Some flavors are smaller. Like some flavors are like free RTOS is going to be super small. And if you have something that just needs timing, and you're not going to have lots of like threads doing lots of things, then you need an RTOS, but you don't need one that is so big. So some of them are much smaller and come with a lot of different features. Like for free RTOS, you're basically doing either like HAL stuff or like it feels like bare metal or HAL. And then for Zephyr, you feel like you're in this. I haven't done embedded Linux, but from the way every time I speak about Zephyr with someone who's done embedded Linux, they find parallels that look like. So it feels like you have this operating system that has, yes, exactly. The way I can do logging out to UART without doing code. So Zephyr feels like this operating system that has primitives that you can use, and you can do this from like, you could ideally, the deeper we go into Zephyr, hopefully the next time I'm doing a presentation, it will be something like adding hardware or something. The deeper we're going into Zephyr, it will get to a point we'll be able to add hardware by using our kconfig, and you could do this deeper and deeper. So meaning Zephyr is big, and you need something small, and you could choose depending on whichever one. Also, time to market. How quick are you going to finish? Are you going to learn something new, or are you going to use a trusted tool that you can deliver it reliably and go with? Yeah. Negative priorities like sudo. Yeah, but they're normal, aren't they? They're normal. In bare metal, they're there as well. There's negative priorities everywhere. They're normal. Okay.
Cool. I think we may have skipped a couple of things, but I think you might have addressed them. I just want to make sure, Zach, that all your slides here you got to speak to. For those of you who are interested in ripping some of these slides, I put them in the handouts portion of the tool, so you can check that out. And then I've also been adding some links. There's like Percepio Tracealizer, and then of course that Nordic course. But did you go through everything you wanted to, Zach?
I think so, yeah. I was hoping to do less code and more explaining of the scheduler rather than, because I can show code for days.
Yeah, no, that's perfect. I think this is really good. For those of you who are unaware, we do have another segment called Engineering Hours, which is usually on Sundays in the at the same time slot actually, and that's where we're going to try and push a lot more of the hands-on stuff. So we're hoping to make these a little bit more, like classroom type sessions, conceptual, and then you can get your hands dirty on Sundays. So thanks a lot, Zach. I mean, honestly, this is a great succinct way of discussing and learning about Zephyr scheduling. If you guys have any questions, feel free to drop them in the chat, or even better, put them in the server so that everybody can benefit from the discussion. That's at discord.gg/devheads, which is D as in dog, and then V as in victory. When you asked Ming how he said his name, I was like, I don't know how many different options there are. Anyway, speaking of inside the server, there are a couple of questions. We've done an awesome job of making sure everybody's getting some help, but here are a couple that are outstanding. How is different programming with an RTOS compared to bare metal coding on AVR? It's kind of a general question, but a question nonetheless. And then there's another one that came up more recently, is an inability to retrieve data from an RS-485 flow meter. You can check those out in the server at those links. So coming up, key card. That's a new tech, key card. I'm gonna talk to Hemel over the next week about KeyCAD versus Altium, because he's used both of them, and so I think this is an important distinction. One of them's free and open source. One of them is for power users. Then July 5th, there's going to be an off week. That is holidays here in the States. The next engineering hour this Sunday, I'm going to reheat the DMA session that we did last Sunday. We had some technical difficulties, so Edison put a lot of hard work and effort and time into a pretty awesome presentation explaining DMA and how it can help advance your designs, especially if you're starting to head towards commercialization. So I'm going to run that at the normal time, 8 a.m. Pacific, 1500 GMT. So if you want to catch that, you can catch it there, and then we'll be getting all this stuff loaded up onto YouTube and other places where you can capture the recording if you want to see it. Then the following Sunday, June 30th, and this is actually for you, John. He was asking questions about what threads are and differences between them. We're going to start the next block of engineering hour sessions. So these are kind of organized things to mesh into these blocks that are logically related to one another. We just went through protocols, but now we're going to start heading towards Zephyr. Actually, we're kind of heading at RTOS from two different directions. So Edison's going to come back and he's going to talk about clocks and timers, which obviously is fundamental when you start building up towards the need for an RTOS. So John, like the way this is going to work is that we'll go through clocking and timing, and then that'll lead into managing some peripherals, like introductions to peripherals like ADCs and PWMs and management of those. And then from there, Umesh is going to come back in and talk about interrupts. So interrupts are obviously, a precursor on the road to needing some more advanced scheduling. So that's how we'll address those. We've got a ton of different kit reviews in progress right now. You can see the 4 of them that are there. These are pretty in-depth. I don't know if you guys have seen the kit review sections on the website, but Navadeep and friends have been doing a really good job diving in depth into these kits and providing a resource that's not so much as long as the hundreds of pages of data sheets, but good enough to give you a good feel for what you might be getting into if you're trying to evaluate a dev kit early stage. And then there's a bunch of other server events and demos and things that are coming up, so keep your eyes out for that. Now, the next thing is what we can do to get 1% better by next week. What do you guys think?
I don't know. I'll message. So I think we're making too many of some questions they get on the forum too quickly. Some questions are put on forums too quickly.
Oh, I see what you mean. Yeah. So
like the askers are not committed to those questions, so they're like kind of just.
Yeah. The thing is, so with the questions, the reasons that they're being put into the forums is that the forums are where that they're indexed. So when the questions get into the forum channels is how they're getting indexed. So there's a little bit of a process problem here because The question, when there's a bot that does this, and when the bot moves it there, it doesn't, I don't think, inform the original question asker that it has been put there. So sometimes I go back through and I ping people and say, hey, this is here now. But I will talk to Noor about doing that on more of a cadence so that we can get that, so it makes more sense. So yep, I've noticed that too, so thanks for pointing that out. All right, well, I guess we were at 99%, and that was the 1% that we needed. So again, Zach, honestly, thank you so much. It's awesome. It's great to have somebody leading us through learning Zephyr. It looks like an RTOS is going to be sticking around for a while. For everybody else, thanks for bringing your grain of sand. Really appreciate the time and attention and participation in the community. And next week, 1 week from today, we'll be heading into that discussion I mentioned about KiCad. So thanks a lot, everybody. Hope you guys have a great weekend.